Good afternoon, class. Today what we're going to be looking at is perimeter and area of similar figures. Now, as soon as I hear that word similar, it reminds me right away, I'm probably going to be setting up some sort of proportion, because that's what chapter 6 was a lot of ratios, a lot of proportions for the entire chapter, and that was the similar chapter for us. So, as soon as I see this, I already know an idea of what I'm going to be dealing with. That word similar to me is almost synonymous with proportion, because that's usually how I find the problems or solve for them. But remember, similar means that it's the same shape, but different size. So, here's the concept. The areas of similar polygons, this is how it says it for us. If two polygons are similar with the lengths of corresponding sides in the ratio of a to b, then the ratio of their areas is a squared to b squared. Alright, let's put that in words that we can get and understand. If I know I have two squares there, like on the picture, length is a to b, well then I know that the ratio of the areas will be a squared to b squared. Because if I found the area of the small shape, well that's going to be side times side, or a times a, so a squared. And if I look at the one on the right, it's b times b, or b squared. Now the neat thing about this is it doesn't just work for squares, but it works for any shape. If I have similar rectangles, if I have similar parallelograms, triangles, trapezoids, kites, rhombuses, if I know two corresponding sides, a to b, I know the ratios of the areas have to be a squared to b squared. Well, I'm not saying their areas are a squared. I'm not saying that the area of the other one is going to be b squared, but I'm saying that the ratio will end up being that ratio of side. And it is pretty neat. Now, similar, just a reminder, same shape, not necessarily the same size. When you encounter this word, it usually means proportion. Ratio of perimeters is the same as the scale factor. Alright, so let's just write a few of these things down. So, scale factor of left to right is a to b. Now, what if I took the ratio of their perimeters? Remember, ratio basically means fraction or comparison of two numbers. Officially, it means comparison of two numbers, but for us, we're going to usually look at it as a fraction. So, if I look at the ratio of perimeters, well, the perimeter of this one is going to be a plus a plus a plus a, or 4a. So that would be 4a. If I look at this one, it's going to be b plus b plus b plus b, or 4b. Oh wait, 4 divided by 4 will cancel out, so the ratio of perimeters is a to b. Oh, anytime I look at lengths in similar shapes, the ratio or the scale factor of side to side is going to be the same for any length in it. So that means when I look at the perimeters, it's still going to have the same ratio, a to b. It's not saying that this perimeter will be a and this perimeter will be b. Not even close. It's saying the ratio of the perimeters will be a to b. So if I knew, for instance, that the perimeter over here was 16, I would then be able to find the perimeter over here if I knew what a and b were. Because this ratio with the actual numbers for the perimeters is going to be the same as the ratio of their corresponding sides. Now, if I look at their areas, well, ratios of areas, the area over here is a times a. Okay, so the area is a squared. So a squared for that ratio. The area over here is b times b, or b squared. So a squared to b squared. And I don't know how to reduce that, so I'm going to leave it that way. And this is all it's saying, is that the ratio of the length here, of the scale factor, of the perimeters, is the square root of the ratio of the areas. Or if I want to put in that in other words, the ratio of the areas is just the square of the ratio of the scale factor, or the ratio of the perimeters. And there we go. That's the idea. But now, let's just quickly try and find them for each of these cases. Now, for this problem, they give us one of the three, and they want us to fill in the rest. So they say the ratio of two corresponding sides is 5 to 4. Two corresponding sides. Well, that's not areas. That's not perimeters. That must be the scale factor. And yeah, it is. 5 to 4. What is the ratio of perimeters and what is the ratio of areas? Well, this is a length, this is a length, so they have to have the same ratio. So for number 1, if the ratio of lengths is 5 to 4, then the ratio of the perimeters has to be 5 to 4. Oh, and then the ratio of the areas is just the square of that. So 5 squared to 4 squared, or 25 to 16. Either answer. The next problem, they say for me the ratio of perimeters is 3 to 7. So that one should be pretty quick to identify. Ratio of perimeters is 3 to 7. So this is 3 to 7. And they want to know the other two. Well, this is a length ratio. And we know that the scale factor and the length ratio, perimeters, has to be the same. But the ratio of areas is always the square of the scale factor, so it's 3 squared to 7 squared, or better known as 9 to 49. And last but not least is the one that says, hey, we know the ratio of areas is 9 to 4. What is the ratio of the two corresponding sides and the ratio of the two perimeters? So I know this is 9 to 4. Well, the scale factor, to get from here to here, I have to square it. So like, for instance, last time it was 3 squared and 7 squared. Well, to go the opposite way, I have to do the square root. So this is the square root of 9 to the square root of 4. Or, in this case, because the square root of 9 is 3, and the square root of 4 is 2. And then ratio of perimeters is always the same as the scale factor, so 3 to 2. And there we go. We now have a way to compare the ratios of lengths and areas in similar shapes. But we are going to use this to solve for problems. We're not just going to say, all right, what's the ratio of the areas, what's the ratio of the perimeters. The whole point of knowing this is so I can find unknown lengths quicker than having to find every single little measurement in the other shape. So, here's the idea. When we're setting up proportions, the ratios have to follow the same pattern. So, if I would use a scale factor, I can only be doing it for perimeters, lengths, altitudes, side lengths, anything that has one-dimensional length. But if I wanted to find area, I'd have to use the ratio of areas, because area matches up to area, length matches up to length. I have to be consistent in a proportion. I can't ever say a scale factor is going to be equal to the ratio of areas. That's just plain not true. So it has to be consistent. And for these problems, I suggest that you set up a ratio of areas. Now, what do I mean by that? Well, let's look at a problem like the one on the board, or the one over there. They have two shapes for us. A rectangle with us knowing one of the side lengths is 5. And another rectangle, it looks like a bigger one, with one of the side lengths being 8. They didn't give me numbers. And I said the area over here is 75, and I don't know the area over here. Well, the scale factor here is corresponding side to corresponding side. 5 and 8 are on the corresponding side, right? Or at least I'm assuming they are in this case. So 5 to 8 is the scale factor. However, I want to compare this to the areas. So I don't want the scale factor. I want the ratio of areas. So I'm going to use 25 and 64. 5 squared and 8 squared. Oh, if I would go over here and call this x, the actual ratio of areas is 75 to x. Whoa. The ratio of areas according to their side lengths has to be 25 to 64. The actual ratio is 75 to some unknown. Well, these two ratios have to be the same. Because this is true because of the side lengths. This is true because that's its actual areas. So now at this point, I have my proportion. Area ratio to area ratio. Left to right. Left to right. Left to right. I'm good to go. Cross multiply and solve. 25x equals whatever 75 times 64 is. However, I'm going to do a shortcut here. 25, divide both sides. X equals 75 times 64 all over 25. Well, 25 goes into 75 three times. 3 times 64, 192. So when we're setting this up, we're going to look for matching up area ratio using the side lengths and the actual area ratio. In fact, most of the problems you're going to be doing something like this. Alright, so let's look at a few problems. Find the unknown area or unknown corresponding side length. Now, when you look at these pictures, X, Y, Z, any length in there, it's a length. Unless it says A equals blank meter squared, feet squared, centimeter squared. Alright, everything in there is a length because it doesn't have a degree symbol. Alright, all these numbers have been made up, but they're just to try and have us practice for our finding unknowns and to set up proportions. So, for each of these, the idea is to first set up the correct proportion. Now, look, I have two things in each of these. I have one length and one set of areas. One set of lengths, one set of areas. One set of lengths, one set of areas. And in most of the problems you'll see something similar. So if I look, if I'm just going to always go left to right here, I have 15 to x. However, that's the length ratio. For me, most of the time, I'm just going to go immediately to the area ratio. And that's what I'd like you to do. So this becomes 15 squared to x squared. And that has to equal the actual ratio of areas. Well, the actual ratio of areas is 135 to 60. 135 to 60. Okay. So at this point, it's really just a solve problem. The actual ratio of areas, and this is getting the ratio of areas according to the side lengths, those have to be the same. So 225 over x squared has to equal 135 over 60. Cross multiply, I get 135 x squared equals 60 times 225. 60 times 225. 13,500 equals 135x squared. Divide both sides by 135. X squared equals 100. Square root both sides. You have to consider the plus or minus 10 here. However, it doesn't make sense for a negative length, so positive 10. And the units for the length here has to be meters. And there we go. I realize I went kind of fast through that, but that's a little bit of review. Set up the proportion. First find the scale factor with just the lengths, square it, set it equal to the ratio of areas. Then cross multiply and solve. For the next one, let's try this. So right away, identify the ratio of lengths, 9 to 3. So 9 to 3. But I want that in ratio of area terms right away because I always find it easier to take the square than the square root. Because I don't know what the square root of 117 is or z. So let's do this. 9 squared is 81. 3 squared is 9. This has to equal the actual ratio of areas. 117 to z. So, length ratio, 9 to 3. Let's make that an area ratio. 9 squared to 3 squared equals 117 to z. Now, you noticed I didn't simplify here, 3 to 1, because we'll take care of that later. We'll rather deal with the big numbers than potentially making an error somewhere else. Now, if you wanted to reduce it, you could, but I'm just going to keep it that way. 81z equals 9 times 117. 81z equals 1053. Divide 81 to both sides, and you should get 13. And feet squared is already there, so I shouldn't put in my answer. Meters wasn't attached to x before, so I didn't put in my answer. I had to put in my answer here. If I put it in there, I'm being redundant. 13 feet squared, feet squared. Just leave it as z equals 13. But there we go. set up the proportion, and solve. Try this one real quick. See if you get the right proportion. If done correctly, you should have got 5 to y. However, as an area ratio, it's 25 to y squared. The actual area ratio is 400 to 256. If you got this, you understand how we are doing the setup. If not, you might want to just take a brief look back at my very first example and look at that one, because I think I did the best job there explaining. And at this point, it's solved. Cross multiply. So 400y squared equals 6,625. Divide both sides by 400. 16.5625. If I had to take a wild guess, I'm betting it's something like y equals 5.05 or something along those lines. But let's take the square root of that number. Ooh, it's not nice. It's 4.07. It rounds up to 4.07. Units included, they were not, so I have to put feet. There we go. Sometimes you won't get a nice number. Other times you will. Alright. And I realized I did something wrong here. That's why my answer didn't come out the way I was expecting it. Try and find it real quick. If you found it, here it was. I didn't copy it down right. I thought this was a weird answer. Not saying that every single number has to be a whole number, but I messed up. That was supposed to be 256. If you did this correctly, I believe you do get a whole number, and I believe it is supposed to be 4. And there we go. So the actual answer for number 3 is 4 because I made an error right there. Well, not all examples are going to be this nice. Sometimes I give you a word problem, but it's still the same idea. We're going to be setting up a proportion because we know the shapes are similar. And you always are going to want to do an area to an area ratio instead of doing something like trying to take the square root to get back. It's just easier that way. But a large rectangular baking pan is 15 inches long. So if I have a large rectangular baking pan, and I know it's 15 inches long and 10 inches wide, and I have a smaller pan that is similar to a larger pan. So right now I'm going to draw a smaller pan, and I know automatically they are similar. So I'm thinking proportion. The area of the smaller pan is 96 inches squared. Find the width of the smaller pan. You want me to find x. What's that width? Well, if I do this problem like how I've been doing, right away I look at the ratio of lengths. Well, width to width is 10 to x. But we've been constantly going this way. 100 to x squared equals the ratio of the areas. And this is where I run into a problem. I have one of the areas but not both, and I'm not going to have two variables in my problem here. But this area, it's a rectangle. It's a small rectangular plan. Sorry, it's the large rectangular pan. So area equals base times height. The base is 15, the height is 10, so the area is 150 inches squared. Oh, so this, if I went 10 to x, or 100 to x squared, then I know that I should go this way, 150 inches squared to 96 inches squared. And there I go, my proportion's set up. It's solved for x again. So, length ratio, I made it into an area ratio. And then I set it equal to the actual area ratio. Area ratio equals area ratio. I'm good to go as long as it's consistent. Left to right, left to right. Good. So cross multiply and solve. 150 x squared equals 9,600. Divide both sides by 150. 64. So x is plus or minus 8. However, the negative answer doesn't make sense. So x is 8. However, I would say the width of the small pan is 8 inches. And that would be my answer because it was a word problem. And there we go. So again, when you're not given a picture, draw one right away. Large rectangular baking pan. Large rectangle. Put it up there. Similar to a small one. Put it up there. Put in 15, 10 inches. A equals 96. Label what I want to find. And all of a sudden it was pretty straightforward. I should compare 10 to x to get 100 to x squared. I need this area to solve the problem, so let's put it in. And most of these problems that you'll see will be something like this. Alright, here we go again. Another word problem. On a blueprint, the area of a room is 100 inches squared, and the length of the north wall is 5 inches. The actual length in real life of the north wall is 35 feet. What is the area of the room? Now, I haven't drawn a picture, but if it's a blueprint, I like to make it nice and simple myself. I'm going to make it a rectangle, like I have up here. So, they tell me, first of all, on the blueprint, the area of a room is 100 inches. So on a blueprint, it's a smaller one, so 100 inches squared. And the length of the north wall is 5 inches. So on here, it would make sense for 5 inches to be up here. Now, the actual length of it is 35 feet. And I don't know the area, and that's what I'm looking for. So let's call that x. Feet squared. Oh, I'm wondering, am I going to run into an issue seeing I have feet and inches? Well, let's just hold off on seeing if I have to invert, and let's plug it into our problem. What if I did 35 feet to 5 inches? That's length to the corresponding length. Well, area formula, that would be 35 feet squared to 35 feet quantity squared to 5 inches quantity squared, which, if I simplified that, would end up being 35 squared, which I don't know off the top of my head, 1,225, and 5 squared would be 25 inches squared. All right, let's look. The actual area that I'm looking for is x feet squared. The actual area of the blueprint was 100 inches squared. So I went left, right, left, right. It's feet to inches, feet to inches. Oh, those units will work out. I don't have to worry about converting them because of where they are. They match up. It's corresponding. It's nice and neat. So at this point, it's just the normal cross multiply. Solve proportion. 25 times x equals 1,225 times 100, or 122,500. Divide both sides by 25, and you should not be surprised to find 4,900. But that wouldn't be my area, because I'm looking for what's the actual area of the room. The room has an area of 4,900 feet squared. And there we go. This is a little bit tough of a section just because you're dealing with a whole lot of proportions and setting them up. But if you follow what I showed you here consistently, first find the ratio of the scale factor, the lengths, parameters. Then you compare that to area right away. If you're solving for area, you're good to go. But if you're doing something like perimeter, you just use this and treat it like an original problem. That is all I have for you today. Till next time.